Hello and namaste. My name is Brandon, and welcome to the next video in my series on basic time series analysis. In this video, we will start looking at forecast accuracy, so how well our forecast is doing when we go back and measure the errors. So in this video, we're looking at a measure called mean absolute error, or MAE. So grab a drink, sit back, relax, and let's start learning. To get you up to speed if you have not watched the previous videos, which of course you should go back and do, we're looking at the GDP per capita, or gross domestic product per capita, for the country of Nigeria, and it's in constant US dollars. We have the year 2000, where it is $1,451, all the way up to the year 2020, where it was $2,396. On a graph, it looks like this. The question we were asking is, how might we approach making a forecast for the year 2021? Now what we did is use the naive forecast. That's the simplest, most baseline forecasting method. That doesn't mean it isn't valuable. Sometimes the simplest method is the most valuable. All we're doing here is using the actual value from the prior period for the forecast for the next period. So in this case, the value for the year 2000 was $1,451. That became our forecast for the year 2001. We just moved it over. And then we do the same for all the other years. So just over and down, over and down. Then we measured our forecast error, which is just the actual value, which you can see there in the second column, minus the forecast value, which is there in the third column. So for example, in 2001, the actual value was $1,499. The forecast value was $1,451. So $1,499 minus $1,451 has an error of 48. And we go ahead and continue that process all the way down the columns. So that is the background. Let's start talking about forecast errors in general. So we can see here that for Nigeria GDP per capita, we have a series of positive forecast errors, which is there in the yellow, and then a series of negative forecast errors there in the blue. So what we can say is in this section, the actual values were above the forecast values. And then over on the right, these actual values were below the forecast values. So the sign of the error will tell you whether or not the actual values were above or below the forecast. Know your errors, and going forward in time series, the ability to understand the error term and what's happening in them is extremely important. So let's talk about that. The forecast errors actually create a new derivative time series that can be a treasure trove of information for the analyst. So if you think back to our previous slides where we have the table of values, we have the forecast, which is actually a time series, of course, and then the errors themselves are another time series. By looking at just the naive forecast errors, you should be able to reverse engineer in your mind how the underlying time series looks, even if you don't know the data in that time series. In fact, many forecasting techniques do this very thing under the hood. Patterns in the naive errors can reveal trends, seasonality, inflection points, and other data. Also, examining naive forecast errors can help in the selection and interpretation of more advanced forecasting techniques. So a common process is to go ahead and run the naive forecast on a time series, look at its forecast values, of course, look at the errors, and then look at the patterns and the errors. And then based off those patterns, that can point you in the direction of other forecasting techniques and interpretation of the time series. So here we have Nigeria's GDP per capita for the time period in question. We can see a rise and then a leveling off. Now we have the forecast, the naive forecast. If it looks like the exact same line, just shifted over one period, well, that's exactly what it is. It's the naive forecast. So notice that a series of positive naive forecast errors, or under-forecasting, indicates an upward trend in this series. So this yellow dotted line represents the gap between the actual value in green and the forecast value in pink. So the distance between those two is the forecast error. And then on the right, we have a series of negative forecast errors, or under-forecast, which indicates a downward trend in this series. And again, that's just looking at forecast errors. So the gap between the actual and the forecast tells you about trend in this case. So the mean absolute error, this is our forecast accuracy measure we are examining in this video. It's very simple actually. So the MAE is the mean or the average of the absolute values of the forecast errors. We make forecasts for each period, find the forecast error for each period, take the absolute value of each forecast error, sum the absolute valued forecast errors, and then divide by the number of forecast errors we have, or the observations. Very straightforward. Now do note here that the MAE, the mean absolute error, is in the original units of the time series, which in this case is US dollars, which makes it easy to understand, but can limit comparisons with other time series that are in different units or magnitudes. So in this case, if we're looking at a different country or a different currency or something else, that might limit our comparisons. Also, this is not a standardized comparison like a percentage or something. So keep in mind that the MAE is in the original units of the time series. In the right-hand orange column, we have our absolute errors. And luckily this is very simple, so I'm not going to go into Excel and show you how to do it. It's just the ABS function in Excel, and the same in Google Sheets, I believe. So it's just ABS and then whatever value you're looking at. Obviously for the first part of the time series, it's the same as the error, but when we go into negative errors, then the absolute value of those errors turn positive. So here is the formula. So 1, find the forecast error for each period. That is the E sub I in the formula. 2, take the absolute value of each forecast error. That's the absolute value sign there, those 2 vertical lines. 3, sum the absolute valued forecast errors. So that's the green summation sign. Divide by the number of forecast errors, which is in the denominator. And then we have, in this case, a mean absolute error of $76.55. So when we take the mean, or the average, of the ABS error column, it comes out to $76.55. And since it is in dollars, I went ahead and put the unit of dollars in there. Visualizing the absolute forecast errors. So this graph is just the absolute forecast errors. So we have our year on the bottom and absolute forecast error on the y-axis. We can see that as we come along here, we have some pretty large absolute forecast errors. And then we go to around the year 2010, and they start to come up a little bit more, and then they start going down again. Once we get to around 2014, 2015, the absolute errors get pretty small relative to the first 2/3 of the graph. So they do pop up here and there, but in general, the forecast errors are smaller in absolute terms. Then we have the mean of these absolute errors, which is $76.55. On the right-hand side, like I said before, overall, our absolute forecast errors become a lot smaller. Remember what I said before, that examining the pattern of the forecast errors can tell you a lot about the underlying time series. So what does this tell us? Well, the smaller absolute forecast errors tells us that it's a flattening out of the time series, something we call stationarity. So smaller absolute forecast error means there is less distance between the actual values and the forecast values. And in the naive scenario, that is when the time series flattens out horizontally. So just by looking at these errors, you can understand what's going on in the underlying time series. Here is our forecast accuracy matrix for this data. Now right now we only have one value. We have the naive forecast and then now the mean absolute error of $76.55. In future videos, we will fill in this entire chart, this entire matrix, not only for this data, but we'll probably do some other time series as well. So remember, in general, the goal is to minimize the forecast error for the known time series. Then use that forecast method or methods to make forecasts for future unknown values. Not all forecasting and evaluation methods are appropriate or possible for data with certain characteristics. For example, data or errors that have negative and/or values of 0, which we'll explore in future videos also. Evaluation methods are sometimes in different units, like we talked about in terms of here, dollars, or they might be in some sort of scaled value or percentages, or a ratio, or something like that. Therefore, comparisons of forecast error occur within a method. So in this case, when we have several forecast methods like B, C, D, and E, we will look at the MAE column for all of those. We'll compare within a method, or between methods that use the same unit or scale. So other evaluation methods along the top may also use, in this case, US dollars. Then of course we can compare those depending on the context of those dollars. It is very common for methods to disagree about which is the best method for forecasting. So it might be that the naive forecast is the best. Then we might get to forecast method C and then evaluation method 3, and that might reduce our error or give us the lowest percentage, and they can disagree. There is no silver bullet necessarily for the best forecasting method. They can sometimes disagree. Then it'll be up to you as the analyst to decide which ones to share and communicate with stakeholders. All right, that wraps up this video on Time Series 101 Forecast Accuracy, the mean absolute error. So this is just the beginning at forecast accuracy measures. So please stick around for future videos. And as always, thank you very much for watching. I wish you all the best in your work and in your studies. I look forward to seeing you again in the next video. Take care and bye-bye.